All right, get ready, because today we're diving deep into quantum computing.
Deep, deep.
We're not just,
What?
skimming the surface here. Like, you already know that this isn't just sci-fi anymore. But we're gonna really explore, like, the huge potential impact
Yeah.
this could have on, like, everything from medicine to
Medicine
materials.
to AI.
Absolutely. And what's so fascinating is that we're at this point where it's moving from theory to reality.
Hmm.
There's a lot to unpack here. So we're going to be focusing on a conversation between Brian Greene and Seth Lloyd
Yeah.
at the World Science Festival. They really get into
Uh-huh.
the nuts and bolts of how this all works.
Exactly. And to understand what's happening now, we've got to revisit some fundamental quantum mechanics. I mean, remember the double slit experiment?
The classic.
It's classic for a reason.
Yeah.
So picture this. We're firing electrons at a barrier with two slits. Now, logically, you'd think they pass through one or the other, creating like two distinct bands on a screen behind it, right? Right. But instead, you get this interference pattern, like waves, almost as if each electron went through both slits simultaneously. Now, see, our brains want to think of electrons as like, tiny marbles. But that's where our intuition just kind of goes out the window.
Oh, I remember struggling with this in physics class. So how do we actually wrap our heads around this?
Well, you got to think of particles as like waves of probability, like ripples in a pond. These waves can interfere with each other. Green and Lloyd, they use this great analogy. Imagine throwing pebbles into like Central Park. Those waves create an interference pattern, right? And where those peaks align, you have a higher probability finding an electron. Where they cancel out, the probability drops.
Okay. I think that helps, but it still feels so weird,
Yeah.
thinking about something existing in multiple states at once.
It is weird. And here's the kicker, okay? When this probability wave hits the detector screen, it collapses. And you get a single electron at a specific location. But the distribution of those locations, it's shaped by that interference pattern. Even Einstein had trouble with this concept, which just goes to show you how counterintuitive quantum mechanics can be.
It really makes you wonder how much we truly understand about,
Yeah,
the universe.
right. What we observe is a particle, but how it behaves is governed by these probability waves. It's this wave-particle duality that's really at the heart of quantum mechanics.
Okay, my head is officially spinning, but I think I'm starting to get it. So what's another example of this quantum weirdness?
Let's talk about quantum spin. Now, this isn't like a basketball spinning, on its axis. It's a property of a particle that we can measure. Think of it as like spinning up or down. But a particle can actually be in a superposition, meaning it's both up and down at the same time until we measure it.
So it's like it's in this blurry, undecided state until we kind of force it to choose.
Yes. And this brings us to one of the fundamental elements of quantum computing, the qubit. Imagine a bit, the basic unit of information in classical computing. It can be a 0 or a 1, right?
Right.
Now imagine a qubit. That can be 0, 1, or both simultaneously.
It's like our double slit experiment again. Left slit equals 0, right slit equals 1, and both at once represents our qubit.
Exactly. And that's how quantum computers can explore so many possibilities at the same time. A classical computer, it's like a single Gregorian chant processing one note at a time. But a quantum computer, it's like a massive symphony, exploring countless possibilities all at once.
And that's where we start to see the potential power of this technology.
Right, think about it. Every time you add a qubit, you double the number of possibilities the system can explore. With a few hundred qubits, you're dealing with more possibilities than there are particles in the observable universe.
That's mind-boggling. But okay, if a quantum computer is exploring all these possibilities at the same time, how do you get a specific answer? It seems like trying to find a needle in an infinite haystack.
That's the challenge. You have to carefully manipulate those probability waves. Think of it like conducting that quantum symphony. The goal is to amplify the right answer and suppress all the wrong ones, and that's where quantum algorithms come in.
Okay, so we have these powerful qubits, but how do we use them to actually solve problems? What do these quantum algorithms actually look like?
Well, there's specific sets of instructions tailored for particular problems. Like you can imagine them as choreographers, directing those waves to produce a certain outcome. There's some amazing examples already, like Shor's algorithm for factoring large numbers.
Right, that's the one that could potentially break our current encryption methods.
Yeah. Factoring large numbers is something classical computers really struggle with. But Shor's algorithm could do it exponentially faster. Huge implications for, cybersecurity, online privacy, even international relations. And then there's Grover's algorithm for searching huge data sets.
So instead of like sifting through a library, you could instantly know where the book you need is.
Exactly. Could revolutionize everything from database management to, drug discovery. And then there's Lloyd's algorithm. It focuses on actually simulating quantum systems themselves, opening up possibilities in material science, and understanding the universe on a fundamental level.
Wow. The potential applications are incredibly diverse. Yeah. But are there problems that are better suited to classical computing?
Oh, absolutely. This isn't about replacing our laptops anytime soon. Think of it this way. Quantum computers are likely to excel at specific tasks, particularly those involving really complex calculations and simulations.
So it's less about replacing and more about opening up entirely new possibilities.
Exactly. And that's what makes this field so exciting. It's about understanding the unique strengths of quantum computers and applying them to solve problems that have stumped us for decades, maybe even centuries.
Okay, this is where things get really interesting. I think we've laid some groundwork here. But now I want to dive even deeper into some specific applications and how this could impact all our lives. We'll do that in part 2 of our quantum computing deep dive, so stay tuned. Welcome back to our quantum computing deep dive.
It's great to be back.
Last time, we were talking about how quantum computers could really revolutionize things, like medicine and material science.
Yeah, we touched on some of those key algorithms too, like Shor's, Grover's, Lloyd's. It just shows you how much potential there is.
And we talked about how it's not really about replacing classical computers entirely. It's more like augmenting our capabilities. It's almost like discovering a whole new sense, a new way to perceive and interact with the world.
I like that analogy. And one area where that's particularly evident is in drug discovery. Quantum computers could dramatically accelerate the whole process, even allowing us to tackle diseases that seemed insurmountable today.
Okay, that sounds almost too good to be true. How would that even work?
Imagine being able to simulate the complex interactions of molecules at the quantum level. Instead of spending years in the lab, scientists could use quantum computers to design and test new drug candidates virtually and identify the most promising ones much, much faster.
So it's like running thousands, maybe even millions of experiments simultaneously, but inside a computer.
Exactly. And this could help us pinpoint drugs that are not only more effective, but also have fewer side effects. Seth Lloyd, in that conversation with Brian Greene, talked about how understanding these quantum interactions could be key to developing treatments for things like Alzheimer's, which has baffled researchers for, decades.
That's incredibly exciting. It makes you wonder if this technology could really unlock some of the biggest mysteries in medicine.
It's certainly a possibility, and it's not just about developing new drugs either. Quantum computing could revolutionize personalized medicine. Imagine analyzing a patient's unique genetic makeup and then using that information to tailor treatments specifically to them.
So we're talking about like custom designed treatment plans for every individual based on their needs and their genetic predispositions.
Precisely. And this idea of tailoring solutions based on quantum insights, it goes beyond just medicine. Let's talk about material science. Quantum computers could allow us to design materials from the ground up, atom by atom, with properties that were previously unimaginable.
So instead of sort of stumbling upon new materials through trial and error, we could actually engineer them with specific purposes in mind.
Exactly. We could create materials that are lighter and stronger for, airplanes, more efficient solar panels, even self-healing materials that can repair themselves.
It's like stepping into a world where the limitations of material science just vanish. But I have to ask, there's still some pretty big challenges here. We were talking about controlling these incredibly delicate quantum states. How realistic is it to think we can actually build these machines?
Well, it's definitely not easy. Remember, we're battling decoherence, that tendency for quantum states to collapse because of noise and environmental factors. And the more qubits you add, the harder it becomes to maintain that coherence and get reliable results.
So it's like a constant race against decoherence.
It is. Researchers are exploring all sorts of approaches to building quantum computers, each with their own pros and cons. Some are using trapped ions, where individual atoms are suspended and manipulated with lasers. Others are working with superconducting circuits. These are tiny loops of wire, cooled to extremely low temperatures.
So it's almost like there are multiple paths leading up the same mountain.
I like that. And the goal. is to create a fault-tolerant quantum computer, one that can correct for errors and maintain coherence, even with a large number of qubits.
Okay, so we have these different approaches. Everyone's aiming for fault tolerance. But how do we actually program these things? It's not like I can just open my laptop and start code.
Right. It's a whole new world of programming. Think of it as choreographing a complex dance of these qubits. You have to understand quantum logic gates, the building blocks of quantum circuits, and learn how to manipulate them to perform certain tasks.
Right. And then there's entanglement. That's one of those concepts that always trips me up. What does it actually mean? And how does it factor into quantum computing?
Well, entanglement is one of the most bizarre but crucial aspects of quantum mechanics. Imagine two particles linked in such a way that their fates are intertwined, even if they're physically separated by vast distances. When you measure the state of one, you instantly know the state of the other, no matter how far apart they are.
So they have this invisible connection.
Exactly. And this property is essential for a lot of quantum algorithms. It lets us create these intricate correlations between qubits, enabling calculations that would just be impossible with classical bits.
This is starting to sound like something out of a science fiction novel.
I know, right?
But it's real.
It's happening right now, and we're really just scratching the surface of what's possible as the hardware gets better. And we understand quantum algorithms better. We can expect to see even more creative and innovative applications.
Okay, that's all very exciting. But let's shift gears for a moment. Talk about a specific application that I think is on a lot of people's minds. Artificial intelligence.
Ah, yes. AI. The intersection of quantum computing and AI. It's one of the most exciting and potentially transformative areas of research today.
Yeah, I mean, so we're basically taking AI, which is already evolving so rapidly, and giving it a rocket booster.
Exactly. One area where this could have a huge impact is machine learning. Quantum algorithms could allow AI systems to learn from data much, much faster and more efficiently, potentially leading to AI that can reason and problem solve at levels we can barely even imagine.
It's a little unsettling to think about, but also incredibly fascinating.
Oh, absolutely. It raises a lot of questions about the future of AI and its role in society. But before we get too carried away with speculation, let's bring it back down to earth.
Okay, yeah, I think that's a good idea. So we've covered a lot of ground here, from the fundamentals of quantum mechanics to the potential applications in medicine, material science, AI. But I have to ask, when can we expect to see this stuff in the real world? When will quantum computers move out of the research labs and into our everyday lives?
That's the million-dollar question. It's still early days, but experts believe practical applications could emerge in the next decade or two. Some even predict that quantum computing will be as ubiquitous as classical computing in the not-too-distant future.
Wow, that's a bold prediction. But I can see why they'd say that. I mean, if we can truly harness this power, the implications are just mind-blowing.
It's a total paradigm shift, and that's why it's so important to understand the fundamentals. And this isn't just some esoteric science fiction concept. It's a technology with the power to reshape our world in ways we can only just begin to imagine.
Well, on that note, we'll pause here, let you digest all this information. And in part 3, we'll dive even deeper into some specific applications and explore what quantum computing could mean for your life. So stay tuned. Welcome back to our quantum computing deep dive.
Yeah, welcome back.
It's been quite a journey. We've gone from, mind-bending quantum mechanics to building these incredibly complex machines. We've even talked about how this could potentially revolutionize things like medicine and AI.
Right. And in this last part, I want to try and bring it back to you, the listener. How could quantum computing actually impact your life? Because believe it or not, this isn't just, some futuristic fantasy. It's got real-world implications. And they're a lot closer than you might think.
Yeah, it's easy to get caught up in the theoretical stuff. But ultimately, this technology is about solving real problems, creating real benefits for people.
Exactly. And one area where this could have a huge impact is finance. Just imagine quantum algorithms being used to optimize investment strategies, to assess risk with unprecedented accuracy, even create entirely new financial instruments.
So instead of relying on those complex mathematical models that are often limited by classical computing, we can have quantum algorithms that can analyze way more data and make much more accurate predictions.
It could revolutionize how we manage risk, how we invest, even how we understand the global economy. And speaking of the global economy, quantum computing could also really impact logistics and supply chain management.
Okay, so how would that work?
Well, imagine being able to optimize, shipping routes, in real time, accounting for everything from weather patterns to traffic, all while minimizing fuel consumption and delivery times. Quantum algorithms could help us find the most efficient solutions to incredibly complex logistical problems.
That would be a game changer for so many businesses, especially now, when supply chains are becoming more global and interconnected. We could move goods faster, reduce waste, and ultimately create a more sustainable economy.
Exactly. And those are just a couple of examples. The truth is, the potential applications are vast and still largely unexplored. It's like having a brand new toolbox with all these tools, and we're just starting to figure out what they can do.
It's like we're on the verge of a whole new era of scientific discovery, driven by this ability to harness the power of quantum mechanics.
Right. And it's important to remember this is still a journey. We still have challenges to overcome. It's going to take real collaboration across all sorts of disciplines, from physics to computer science, even material science and engineering.
Right. It takes all of us to really bring these innovations to life.
Absolutely. So as we wrap up our quantum computing deep dive, I want to leave you with this. This is just the beginning. I really believe that the next decade will bring an explosion of advancements in this field.
Yeah.
And the implications for society are profound.
It's true. We're witnessing the birth of a technology that could really reshape our world.
And while we can't predict the future for sure, one thing's clear. Quantum computing is here to stay. It's time to start asking ourselves the big questions, to think about what this all means, and to really prepare for a future where the boundaries of what's possible are constantly being redefined.
It's a call to action for all of us. Stay informed, engage in the conversation, and really help shape this technology in a way that benefits all of humanity.
Well said. As we finish up, I want to encourage you to keep exploring this, keep learning, and never stop asking questions.
Yeah, because at the end of the day, that's what this is all about, right? It's about pursuing knowledge, understanding the universe, and using that understanding to make the world a better place.
Couldn't have said it better myself. And who knows, maybe someday, you, the listener, will be the one making those groundbreaking discoveries in the world of quantum computing.
Yeah, that would be something.
Yeah.
Until then.